So what I want to tell you today is the connection between the complex geometry, and I should say Kähler geometry, and the natural motivation of the considering the sub-Riemannian geometry, including the Sasakian geometry, and also the larger class like the H-type population, as Dr. Molina said. So before talking about the blah, 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 so let me give you the reason why one need to care the Kähler geometry to study the Heisenberg group, okay? So let us just look at the following set. So I just consider the set over the complex field, okay? And I just consider the Euclidean space and just consider the uniform without the boundary. So that we know from the differential geometry that we can consider the natural metric that makes this open set to be the complete metric space. Is that clear? And in the framework of the Kähler geometry, it is possible to write down the Riemannian metric as a so-called one-on form. I'll explain this in detail, but this is just nothing but rewriting the Riemannian metric on this specific Riemannian manifold. Is that clear? And with this metric, this manifold indeed becomes a complete metric space, although there's no boundary. And this metric is quite special. So people usually prefer to call this metric by the Poincare metric. And this metric has two special properties. One is that the Holorn sectional curvature, whatever that means, is constant everywhere, which is the following value with this weight here, so that it becomes -4 over n+1. And this metric is so-called the Einstein metric. So as a one-on form, this is proportional to the Lich tensor as also one-on form. So that this Poincare metric is special in a sense that Holorn sectional curvature is constant, and it is the Kähler-Einstein metric. But the more specific feature is the following. This gives the motivation of studying the sub-Riemannian geometry for the complex geometers like me. So if one just look at the topological boundary, then this is just nothing but the bore in R2n, right? So that the natural topological boundary is nothing but the sphere of the dimension 2n-1. This is just obvious. However, what we care, this manifold is quite special in a sense that this is not just a Riemannian. Of course, this is not just a topological manifold, this is a Riemannian manifold, but we'd like to consider the notion of the complex structure. And the part of the definition of the H-type foliation that last time Dr. Molino mentioned is nothing but the generalization of the complex structure from this context. I will explain this a bit later. So that we'd like to view this as not just as a topological manifold, or not even just as a Riemannian manifold. We'd like to view this as a so-called the sub-Riemannian manifold with several reasons. So that this should be regarded as a sub-Riemannian, especially this is a CR manifold. And this is actually more special. This is Sasakian manifold, so that one can take the nice normal coordinate. And now let's just remind ourselves what we learned from the just a naive topology, so that if we consider just a sphere, it doesn't need to be the odd-dimensional sphere, and then we just remove the 1 point. Then we know the notion of the stereographic projection. Do you agree? So in terms of the stereographic projection, we know that if we remove 1 point from the sphere, it should be homeomorphic to the Euclidean space. That's what we learned from topology. But now we want to regard this guy, I mean the topological boundary of the complex hyperbolic space, as an odd-dimensional sphere. And we want to put additional structure in order to say this becomes the CR manifold, so that we want to view, even we remove the 1 point, still as a CR manifold. So if we keep the additional structure, so the corresponding additional structure with the Euclidean space becomes indeed the Heisenberg group. And in fact, this is exactly the case that what if one starts from the boundary that is CR isomorphic to the Heisenberg group, then the corresponding interior is biholomorphic to the complex hyperbolic space. So in order to study the classification theorem of the complex geometry, it is natural to look at the CR geometry, especially which CR manifold is CR isomorphic to the Heisenberg. This is exactly the same question, which corresponding interior is biholomorphic to the complex hyperbolic space. So that this gives the natural motivation to study the Heisenberg group, because especially the CR structure, because CR structure of the Heisenberg correspond to the natural structure of the complex hyperbolic. This is one of the motivation. Is that clear? And in order to study the CR structure, one needs to study the notion of the sub-Laplacian on the Heisenberg group. And from there, there are lots of stories, including the H-type relation. So that's the motivation. Is that clear? So that in order to define the CR structure, one needs to look at the geometric data of the complex structure here. So that's why we first need to look at the the some necessary structure of the complex geometry to see where the generalization over here should actually come from. Is that clear? So in this viewpoint, if you look at back the definition of the H-type foliation that Dr. Molino said last time, so there was a notion of the generalized complex structure. This is nothing but coming from the complex structure from the interior. It's actually nothing but just a continuous extension, to be honest. So this is the motivation that why want to mention this. So one of the practical part eventually is that if one want to study the Heisenberg group or the CR manifold in general, then one can just look at the corresponding interior. Then there is some nice geometric understanding already. Then from there one can extract the data on the topological boundary that becomes the CR manifold or the Sasakian or the H-type foliation. And another nice perspective, if we're talking about the complex manifold, is that, so although I identify the topological boundary of the complex hyperbolic space as a ortho-dimensional sphere, one can view this as a complex Hopf vibration, which is the positive curvature model of the sub-Riemannian geometry. And then there are lots of the identification explicit, not just the identification, but also one can construct the explicit map. At least in the case of the Heisenberg group, so that one can use the bunch of the identification to study the Heisenberg in the totally different context and different perspective, but all those businesses are closely related to the Kähler geometry. So that's why I care. Is that clear? So rather than just thinking about the details, I just want to...
Sorry for the interrupting. Can I ask one quick question?
Sure, absolutely. Yeah.
Yeah. So you mentioned about the complex, the hyperbolic space, and this reminds me that whenever I took my graduate courses, the instructor told us something about the basic hyperbolic space is like considering the upper half plane of the complex plane, and she showed us how the geodesic on that the upper half plane looks like, and mentioned that the metric we are using is the Poincare metric. So is this hyperbolic space has a relation to the list of the hyperbolic spaces you have just mentioned?
So that's really good question. So I'd like to address the question in this manner. So one can just replace the field from C to R to consider so-called the real hyperbolic space. This is also another model space in Riemannian geometry, which has the constant sectional curvature, which is negative. Mm-hmm. But one can consider so-called the notion of the Kähler transform. And the Kähler transform is indeed the isometry from the upper plane model to the Bohr model. And this works for both R and C. On the other hand, if one just extract the topological data, topological boundary, this is just nothing but the sphere for both real hyperbolic space and the complex hyperbolic space. But the special feature of the topological boundary of the complex hyperbolic space that should not be the case for the real hyperbolic space is that, so as a topological boundary, this is just clear. So it's just should be the topological sphere. This is clear for both cases. But we have the additional structure that today we'd like to just see briefly, so-called the complex structure. And if one put the complex structure, then we should regard this as a Heisenberg group, which has a group structure. So the group structure of the Heisenberg group is naturally coming from the complex structure of the complex hyperbolic space. So that if one replace this to be the real hyperbolic space, so we don't require the group structure for the boundary of the real hyperbolic space. So the natural group structure of the sub-Riemannian geometry is naturally related to the algebraic geometry feature of the complex geometry in some sense.
Yeah,
so
for your answer. Mm-hmm.
Yeah. So that the notion of the complex structure should be super crucial in Kähler geometry, definitely. So, and we already generalize this as a generalized complex structure for the H-type foliation, of course, including the Heisenberg group. So, but the intuition over here is so easy. So we are just looking at the rotation by 90 degrees. That's our reality. So that we consider just nothing but the real smooth manifold. We can weaken the regulatory assumption here, but we don't care. So that it just start from just a smooth, just differentiable manifold, so that we can consider the notion of the endomorphism. But this just means that for each point, we can just consider the map between two fibers. such that if we just compose twice, then it becomes minus identity. And this is exactly the case of the just a imaginary number, right? I squared is equal to -1, and it's just nothing but the generalizing the notion of the imaginary number, so that we are just defining the complex structure, almost complex structure, by just looking at the imaginary number. So the intuition is super clear. And as long as we require this condition that this map must be surjective, for example, and so that one can just extract the necessary properties from here, but this is just obvious. But the way of the view with this complex structure for the smooth manifold is the following. So still we are considering nothing but the smooth manifold, so that we just allowed to get the almost complex structure, meaning that we have just a bundle endomorphism satisfying this condition. And what we want to do is that we want to change the base field from the real to the complex. And in order to do that, but still we'd like to keep all necessary geometric data so that we can still do the Riemannian geometry. So that start from just the real tangent bundle. We know what this is, right? So that let's just assume that we know what the real tangent bundle should be. And in order to consider the complex, it is at least algebraically necessary to consider the notion of the tensoring by the complex field. In order to introduce the complex numbers, right? So that we just change, for example, Rn to Cn. That's the reality. In order to introduce the complex numbers. So, but the reality is that for each tangent vector or the vector field, that we just tensor by 1. So we just map from here to here in this manner. And once we equip with a tensor with the complex field, then we can split this complex tangent bundle into 2 pieces. And people prefer to call this by 1, 0 part and 0, 1 part. But the reality is that we can actually show that easily, that this J has 2 eigenvalues. One is I, the other is minus I. So each of them are just eigen subspaces for each of the I and minus I. That's the reality. And if one just put the conjugate bar, then one can go from one to the other. So the complex bar is just isomorphism. And the reality is that we just split X tensor by 1 in this manner. So those are actually the same. But the reality is the following. And especially we'd like to just consider the projection from here to the first component. So what happened here, fiber-wise, is the following. So we consider the n-dimensional Euclidean space, and we just make the dimension twice. And then we just split into 2 pieces. So as a real vector space, those 2 are same as a vector spaces. And the way of the map is we map from X to here, because we just split this element in this manner, and we just decide to assign each X to be this guy. But the reality is that if you consider like the ddx or ddy, then ddx correspond to ddz, because now we work over complex field here. And ddy just maps to ddz times the imaginary number. So if this is a real 2n-dimensional vector space, this just becomes now n-dimensional complex vector space. But over R, those are the same. So that we have just nothing but the R linear isomorphism from here to here. But now we just change the perspective from the real vector space to complex vector space. Is this clear? But there is a one necessary consideration in order to do the geometry. So that for the tangent bundle, real tangent bundle, we needed to consider the notion of the Lie bracket and also the Lie derivative. And in order to do that, as long as we'd like to transfer all geometric data from here to here, then we also need to preserve the Lie bracket. But this is not generally the case for the arbitrarily almost complex structure. So that we'd like to put the additional assumption on the almost complex structure that also preserves the Lie bracket structure. In other words, we'd like to say this map becomes the Lie algebra isomorphism, not just a vector space isomorphism. In such a case, we will call such a J the complex structure. So that there are lots of the, I think all of you already solved this from somewhere, and I don't care the proof. So we know how to define the complex structure from the choice of the almost complex structure. There are a bunch of the like the equivalent descriptions, so that we will just accept one of the condition here as just a part of the definition for the complex structure. So that we will only work on the J in our case, and in this is also, it should be comparable with the almost complex structure for the Heisenberg group, is that we will just work on the complex structure. Without it, and otherwise we should mention. Is this clear? So that I will consider the pair. One is the smooth manifold, and another one is the complex structure. So that I also don't need to worry about the preserving the Lie bracket structure. So that as long as so this just means the following. So I choose arbitrarily 2 vector fields from the real tangent bundle. then I can consider the Lie bracket. That also becomes another vector field over here. And if I just transfer all data to this would be called by the holomorphic tangent bundle. So that if I just move all data to the holomorphic tangent bundle, still the Lie bracket should be preserved by the holomorphic tangent bundle. And in such a case, we will call such a corresponding J should be the complex structure. And the pair of the M with J would be called by the complex manifold. And in general, there are infinitely many complex structures. This is the heart of the matter for Kähler geometry. Even for just a real two-dimensional tori, there are uncountably many complex structures that makes the complex tori to be not biholomorphic to each other. Topologically, they are exactly the same, but biholomorphically speaking, they can be different and they are uncountably many. So far, so good. So that we need to consider the notion of the complex structure in order to study the complex manifold, but still we are just considering the special class of the Riemannian manifold, to be honest. And we just want to look at the topological boundary, and we will just put the additional necessary structure to just make the comparability between the complex manifold and the topological boundary. So the way of the doing is to by introducing the notion of the Kähler structure. So, but again, the reality is that we just have the special kind of the Riemannian manifold, to be honest. So that let's start from the complex manifold. So that the complex structure is usually called by the integrable almost complex structure whatsoever, but let me just call this by the complex structure so that all necessary conditions should be required. So what we will do is the following. So we still just work everything over R because this is just nothing but the smooth manifold. So that I will just give the Riemannian metric. And now let me just assume that we are already familiar with the intuition about the Riemannian metric, so that we just need to want to describe the shape nicely from the data of the family of the inner products, right? So that we will require the metric G. This is in general not true, but we will just restrict the class of the Riemannian metric that the Riemannian metric is compared with the given complex structure. This means the following, so that we want to treat this as an orthogonal transformation for each fiber, so that this just means that we consider arbitrarily tangent vectors or the vector field, then this is always same with putting the J at the same time. So that we will only care such a metric, and this metric is usually called by the Hermitian metric on the complex manifold. So this is more special one. But the reality is still we are just considering the special type of the Riemannian metric. So still we want to make everything to be exactly the same as the Riemannian geometry. And this is a way of the doing. So that's the reason that I need to say this is a Kähler, not the non-Kähler, because otherwise I need to introduce another connection that would be called by the Chern connection, right? But in the case of Kähler, it's just the same, so that we don't need to worry about whether or not they're the same. So we know what the Leibniz connection should be from the Riemannian geometry side. So as long as I have a Riemannian metric, then I can induce the unique metric, as also Dr. Molnar said last time. And in the case of the Kähler, this connection is also comparable with the complex structure. This can be proven, so that we will only have one necessary connection, which is nothing but the Leibniz connection, which is also comparable with the complex structure. And the community of the Kähler geometry called this connection to be the Chern connection. There's a way of defining this outside of the Leibniz connection, but we will not care as long as I just care the Kähler manifold. So that I can just consider the same Leibniz connection. So all the different point is the following. So we just change the field from the real to the complex. That's the only difference. So for example, I have the R linear like the 2 tensor G, and also we have the notion of the affine connection. In this case, this is a Leibniz connection, but we will just extend them C linear way. So this just means that without putting the bar, so that we can extend everything, right? So why not? So if you just allow this condition, for example, then you can see something happen. So for example, so we just change in this context that we change ddx to be ddz and ddy to be I times ddz, so that they were linearly dependent here, but over C, over a complex field, those are now linearly dependent. So all we need to care is each pair determine only one vector. Is that clear? So that 2n-dimensional real vector space now becomes n-dimensional complex vector space. That's the real difference. So that I just need to care just one vector over a complex field. So in such a case, the basis of the holomorphic tangent bundle, I mean T10, should be generated by n tangent vectors over R. But now I want to consider this guy. So this guy means this one. this whole, not this before this after the split, so that I also need to care the complex conjugate here, so that those two n numbers of the vector field will generate the whole tangent bundle with the tensoring by C. But this is not T10. But if you just look at this part, what you can notice is that let me just put those vectors on the Riemannian metric, satisfying this condition. But what I said is that I can always put the complex structure freely. So those two must be the same. So, and this is already assumed. But what we already know is that those are the element of the eigenspace that makes J. So that this is just the I just becomes the eigenvalue. So that there is just an I and there's another I here. So that you can take it out. So that it becomes just a minus same one. So that it becomes 0 because they just the same except the sign. The similar work show that if you plug in the two vector field with the complex conjugate altogether, this must be 0. So our non-trivial term should be the case that you need to plug in one without bar, the other one with bar. This is the only term that should be survived. And this is just nothing but the component of the Riemannian metric. Is that clear? And you can also show that I put here to be without bar, and here's a bar. And if you just change this notation, so you can actually notice that you can also put the complex conjugate here. So this can be also seen easily. So that what you can notice here is that so the Riemannian metric component can be written in this manner, and one vector field required without the complex conjugate, the other one required the complex conjugate. So people prefer to describe the Riemannian metric rather than as just a two tensor in Riemannian geometry. We prefer to write in terms of the differential two form, and one differential form do not contain the complex conjugate, the other one contains the complex conjugate. And each of them correspond to Gij bar defined in this manner. And some of the classical reference call this by the fundamental form, and I prefer to call this by the Kähler form, or just some paper just write this as just a Kähler metric, although I didn't define the Kähler yet. But the reality is that we also use the notation omega, but the reality is that this is just nothing but the Riemannian metric. Instead of writing as a two tensor, we just prefer to write this as a differential two form. The reason is that if we write down the Riemannian metric as just two form, then we can take the exterior derivative. That's our reality. So that the definition of the Kähler metric omega is that this omega is D-closed. That's the definition. And in the case of the Sasakian, also there is a certain analog from here. So we consider the Riemannian metric as a fundamental form. That means it's just a two form. And then we require this to be D-closed. The reason is the following. So, and I'd like to explain in the view of the differential geometry. So as long as we care the Riemannian geometry, so although we are saying blah, 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 but the reality is that we should know how to calculate in certain coordinate. And always the messy issue is that we should choose the so-called geodesic normal coordinate in order to make the crystal symbol to be vanished at that point. So if the crystal symbol is vanished, and this coordinate can be chosen by using the geodesic, but such a coordinate should be actually just a smooth coordinate. But as long as now we care the complex structure, we need to care the much stronger structure that would be called by the holomorphic structure, right? So that geodesic normal coordinate cannot be used in the category of the complex manifold in general. This cannot be done. However, one can ask the following question, so that still we are considering the Riemannian manifold. So what if we have the holomorphic normal coordinate? That means that at that fixed point, the crystal symbol is still 0, but we are making every coordinate to be biholomorphic. This is exactly equivalent description of d omega equal to 0. So the Kähler condition is nothing but taking the holomorphic normal coordinate on each point arbitrarily. So let me just summarize again. In Riemannian manifold, for each point, we can always take the geodesic normal coordinate to make the crystal symbol to be 0 at that point. But this context should be considered in the smooth category. And if one considers the holomorphic category, then one needs to put the additional structure from the complex structure. In that case, if one put assign the holomorphic normal coordinate, meaning that each point we can make the crystal symbol to be 0, then this condition is exactly coincide with this guy. So I prefer to just interpret this rather than the symplectic condition. So this is usually called by the symplectic condition in many textbooks, but I think this is more intuitive. Is that clear? Of course, one need to prove it, but this is just a classical result, so that one can just accept this as a fact. And so let me know if you have any questions so far. And otherwise, I just want to mention that's just one of the well-known form of the certain curvature tensors. That might be later on just used as just a fact. So far, I try to explain the necessary ingredients. One is the complex manifold, complex structure, and the Riemannian metric that we will call by the Kähler metric eventually. And this connection is nothing but the Levi-Civita connection. And if we make this to be just a non-Kähler Hermitian manifold, then one should change the connection. But in our context, I think we do not need to care. And then we will just require this additional condition to consider the notion of the holomorphic normal coordinate. Yeah, let me know if you have any other questions. So otherwise, I will just keep going. So one important feature that you can see is that, so we have the way of the writing the Crispus symbol. So Crispus symbol is just the coefficient function as a linear combination of this expression, right? This is very known. And that's just working on the expression. Then what one can show is the following expression of the Crispus symbol, so that still we are just working everything with the Levi-Civita connection. So we already know how to describe the Crispus symbol in the real coordinate. But if we change the complex coordinate, then one can prove that each gamma KIP, for example, can be written in this manner. And what you can see is that, so there are two indices for J, so we need to take the summation for J, and we have this expression. So it looks much simpler than the Crispus symbol expression of the general Riemannian case, but still you can prove this one it should be the case. And let me just accept this formula as just a fact. So that if you are curious about the proof, then you can just check the line by line. And then we are still working everything with the Levi-Civita connection, so that we also know how to define the curvature tensor, right? Either as a 3-1 tensor or 4 tensor, whatever that means, we don't care. So that still we have the following, so that especially in the case of the Lich tensor, so Lich tensor is a 2 tensor according to Riemannian geometry, so that we can just put one without bar, the other one with bar. Then one can prove that this has a really nice expression as just a log of the determinant of the metric with the like just a Hessian. So just taking the partial derivative with respect to J and K bar. So the expression of the Lich tensor is much easier. And this has a huge implication in complex algebraic geometry, in a sense that this can be realized as a first Chern class of the canonical bundle. But there's a lot of the algebraic generalization from here. But in Riemannian geometry, so we know what the Lich curvature should be, and the Lich curvature can be written in this nice manner, of course, with the local coordinate. Of course, I took the local coordinate from CN, but still, this is the case. So the important question related to Sasakian geometry is the following. So I time to time explain this to the people who are interested in complex geometry, and the necessary details should be filled to the student who want to study complex geometry. But as a fact, this is one of the most important facts in Kähler geometry, and Professor S.T. Yao got the Fields method from this result. So the context is the following. So one want to find the nice Kähler metric in the following manner, so that just put the compact condition. So this condition really matters because in our manifold, this is not compact. So after getting this result, so complex geometry try to just eliminate this condition under the reasonable condition, like the bounded geometry or whatsoever. So consider the compact Kähler manifold. And what one can notice is that, so what we made over here is that the Kähler metric is already declosed. So that this is the differential two form, which is declosed. So that one can realize the Kähler form as the element of the second rank homology. And with this description of the Lich tensor, so whatever the way of the proving, so from here, one can also realize the Lich tensor for the Kähler manifold is also closed two form. So Kähler metric and the Lich tensor are the element of the second rank homology class. So this is super nice. So that one should ask the converse question in a way that if one starts from the Kähler metric, which is a closed two form, then one can associate the Lich tensor, which is also closed two form. So that what about the converse? So that let's just start from the element from the second homology class. So just choose any element from the second homology class, so that one should ask, then is there a metric which is Kähler, so that this is declosed, so that the corresponding Ricci curvature is exactly coincide with this omega. Sorry, this rho. So the question is now the converse. So for each scalar metric, which is D-close, then it associates the scalar two form, which is D-close. So that if one start from the any element from the second cohomology, then is it possible to find the scalar metric that makes a Ricci curvature to be exactly precise this rho, and they have the same cohomology class? And this is a question that Professor Yao confirmed. So that one just need to solve so-called complex Monge-Ampere equation in order to get this answer. So the question is yes. So there is such a metric, and such a metric should exist, and this metric should be unique. So that what one reduced the problem from the contribution of the Yao is that one just indeed need to solve this type of the second order for nonlinear differential PDE. So that what one can say is that we start from the base scalar metric. So omega, and let me just write down the omega naught, the component by Gij bar. And we are looking for the new metric omega that makes this condition to be happen. So that let me write down this omega in this manner. This just means that we are choosing the scalar metric from the same cohomology class. Of course, one need to show why the dilemma can be just considered instead of just a D exterior derivative, but this is actually quite important for, so this is from the Cauchy theory, so that I want to mention this more precisely. So that one want to define the scalar metric in this form, but this can be written as this PDE. This is called by the complex Monge-Ampere equation. And what just the Professor Yao did is just he just solved this PDE. So the reason to care this type of the equation in this context, so I just want to mention this as a last remark, so that one already solved the complex Monge-Ampere equation for the compact scalar manifold, and there are lots of the different techniques. So one can just solve this Monge-Ampere equation from the so-called elliptic method. So this is just means the priorly estimate, so one can just get the equation from the continuity method. Another one is one can use the Kähler-Lisch. And if one cares the algebraic geometry, so there are the classification of the algebraic varieties in terms of minimal model, and the minimal model can be approached from the Kähler-Lisch flow perspective by just solving the complex Monge-Ampere equation. So that this also matters for the classification. But the matter is that if one then try to solve the Monge-Ampere equation for the non-compact Kähler manifold, then the same method in general does not work. So that one need to worry about the boundary condition. And this boundary condition in many textbooks that you can find if you just try to search it. So let me just show you. Actually didn't prepare the reference, but I think I can find it easily. So for example, so there are lots of the literatures that you can find for the CR geometry with many different contexts. And for the CR geometry, the most primary model should be the Heisenberg group. So always, as long as people care the CR manifold, for example, here. So the CR geometry is just for the introducing why the horizontal distribution should be considered. However, that is coming from the CR boundary, from the complex manifold. And the original context is coming from the fact that one want to solve the complex Monge-Ampere equation. Where is it? I think I can find it. So that I just show you the classical case, but one can just reduce the complex Monge-Ampere equation in some nice manner. So from the Pfefferman's contribution whatsoever. And then in order to solve the complex Monge-Ampere equation on the boundary, then one need to look at the CR data. So CR structure really matters. And from there, one can solve the Monge-Ampere equation. So that the understanding of the CR structure really matters to study the complex geometry. And if someone cares, then I can definitely try to explain the deeper connection. So like digging through the relation between the complex Monge-Ampere equation that I explained really naively. And what you can see, for example, I think I can find the theorem. Yeah, so for example, in order to deal with the boundary data of the complex Monge-Ampere equation, so this M just corresponds to the CR boundary, and the information of the CR boundary corresponds to solving the complex Monge-Ampere equation. And in this manner, there's the Sasakian flow or CR flow that's would be also studied by many people in geometric analysis, is closely related to the understanding the Lisch flow. So that this is also still one of the active research field. So yeah, so I'm not sure that I should explain in this direction for our seminar, but at least if you want to like make the connection between the complex geometry and Sasaki geometry, then you can find lots of the literature. And if someone wants to, then I can try to present something. Yeah, so those are what I want to today just mention, because some of you might want to like see the big motivation why I need to care the sub-Riemannian geometry, and the primary model case is the CR geometry, and it's coming from the Heisenberg group. It's coming from just the topological boundary from the complex hyperbolic space. This is one of the standard motivation. So this is what I prepare. So let me know if you have any questions.
Can I ask you one question?
Sure.
Yeah. So actually I'm the beginner of this
Sure.
yes the Keller geometric setting. So my question is, the actually the as you have seen in my talk last time, if I study geometry, I take care of the reading the geometric data from the operator encoding the geometry data. Well, in the case of the Riemannian manifold, the Laplacian associated with the Riemannian metric plays that role. So, can we expect that we have such kind of the differential operator encoding geometric data in the setting of this Keller geometry?
So I also want to listen the perspective from Dr. Molina for that important question. So here is my naive thought. So when I investigate the some sub-Laplacian in certain reasonable class in sub-Riemannian geometry, so there's always the sort of the nice analog from either the Riemannian geometry or the Kähler geometry. And the geometric, like the behind implication of the sub-Laplacian and sub-Riemannian geometry usually appears from somewhere already. So that one want to first understand those classical known cases to understand the geometry feature. And if one try to extend the result to the sub-Riemannian context, although people believe that because the geometry context should be just transferred from here to here, so that one should be able to prove something interesting. But the reality is not that really easy, to be honest. So it's not just really about the naive one-to-one correspondence, but it's really something that one need to dig to get something new. So that one can always find some natural analog from the sub-Laplacian to some natural elliptic second order operator, or even the sub-elliptic, but just the comparing and the get the result is not trivial at all.
Yeah,
but it
course.
happens time to time. And I just want to listen Gianmarco's perspective. What do you think?
Yes, I mean, I agree with everything you're saying. So I don't, something that I'm not as familiar with is the full suite of types of geometric information that people try to get from the Laplacian. But the motivating reason to study the Laplacian from my perspective is to try to understand geodesics. I know this extends to a lot of the other things that you use. And this is exactly what I was planning on talking about, but it turns out that if you try to use the Riemannian understanding of the Laplacian, you run into an issue specifically because the sub-Riemannian metric is degenerate if you try to consider the tangent bundle as a whole. There are ways to fix this, and what you can show is that by modifying the definition, at the highest order, your new definition of a Laplacian still contains the same information. The question is just what happens to these lower order terms and how do you work with it? But that's exactly what I want to present. So the answer is yes, you can still get a Laplacian. Yes, it still has most of the relevant information, but it's an extremely subtle thing. You have to do some work.
Yeah, so if Gianmarco wants to present something today, then it will be good. Or we can just move to the Dr. Li's talk. So Gianmarco, you can decide.
Did we want to take a break, or is this the right moment to continue?
It's up to you. It depends on the time of the presentation. So how much do you want?
I'll actually go ahead and present what I just said, and I'll be brief, and then we can decide which, if any, directions would be good to. Okay. There. So we're trying something new today. Instead of a beamer, I'm going to stream from this device just to check, because it's the first time I've done this with this. You can see what I'm writing? Okay, excellent.
Yep, yes, I can.
So then the idea, which I'd like to go over, is exactly how one constructs the sub-Laplacian and why there is a problem. And in order to understand that, I think it's necessary actually to start from the notion of Hamiltonian mechanics. Like where does the Laplacian even come in the first place? How do we motivate even in Riemannian geometry? So the idea then is that if you have a curve gamma, so I don't know, some small interval, let's say, into your manifold, we call it a length minimizer, of course, if it minimizes length in some small interval. And there's the standard Riemannian result that you can say that length minimizing curves are always geodesics. So here, geodesics are defined as satisfying a certain nonlinear second order differential equation, the geodesic equation. So the question is, can we generalize this? Can we use this in sub-Riemannian geometry? And the first thing you have to understand is that in order to deal with length minimizers, we need a definition of length, of course. So we start from the idea of saying that gamma as a curve in sub-Riemannian geometry is horizontal if we know that gamma dot is always in our distribution. So what I mean by this, of course, is that we have the pointwise distribution that defines the sub-Riemannian structure, and we insist that gamma dot is in this, I can say almost everywhere. Of course, to explain almost everywhere, we have to have a definition of measure, which a priori we don't. But what you can do then is, well, there's several different perspectives you can take, but the Hamiltonian mechanics, which I guess I won't go into too much detail. I think you can argue that this is originally motivated from physics, but the Hamiltonian mechanics go something like this. It appears a priori that one should be working with tangent vectors. You have because the idea being the tangent vector is corresponding to velocity of a curve from a physics perspective. But the Hamiltonian mechanics says it's actually more natural to consider cotangent vectors. So the idea is, given some function, usually denoted h, that goes from the cotangent bundle of a manifold into, say, the real numbers, which is called a Hamiltonian, then one can consider several constructions that come from this. You first define a vector field on the cotangent bundle. So this is a smooth vector field over T star M. So we're on the tangent bundle of the cotangent bundle of your manifold is defined, I should say, by such that the differential of the Hamiltonian that you've chosen is as such. Now here, this is the canonical symplectic form on T star. And if you haven't seen this, I think because it's a little sort of back and forth, I won't go into it too much at the moment. I can talk about this at length, but the whole idea is that given any manifold, the cotangent bundle has a canonical symplectic form. Interestingly, that doesn't extend to the tangent bundle or anything like this. So yeah, it's an interesting construct. So the situation is that we take this canonical symplectic form, you choose any function h that goes from the cotangent bundle to R called a Hamiltonian, and then define this called the Hamiltonian vector field. And what happens then in Hamiltonian mechanics, you use a Poisson bracket structure that shows up because of this, and you can show that if we define a bracket in a convenient way. So I want to give you the proper definition, which I had pulled out for myself. Grab this page here. Yes, there we go. So the idea then is that we define a bracket using Poisson brackets, FH to be equal to the sum cross I. So here I goes from, I'll say 1 to the dimension of the manifold. You take the partial derivative of your function with respect to xi, partial function of the Hamiltonian with respect to qi. I will define these in just a moment. Qi, partial Hamiltonian, partial xi. So here, xi, qi, which actually, if I'm going to follow the Newtonian or the tensor algebra notation, the q's should have subscripts. So let's just establish that right now. Are the canonical coordinates on the cotangent bundle. So far this is okay, and this is just a definition. So then what happens is working through the vector fields that are generated by Hamiltonians, you can come to understand that for any so let's say this, for any function, let's say f of t defined along an integral curve of the Hamiltonian vector field. So the idea here is you've got this Hamiltonian vector field on the cotangent bundle. It has integral curves. That is just the standard solution of the border or the differential equation that makes these the tangent vectors. The derivative with respect to time of f of t is actually equal to this bracket. So it's just a really nice, basically it's a nice observation you can make about integral curves and functions defined along them. So what does this lead to? Well, you can show in Riemannian geometry that one can define a Hamiltonian. So I will give this in terms of these standard coordinates. Right, they don't use P, that's fine. So here you are trying to define a Hamiltonian, that is a function of the cotangent bundle. So at x, which is in M, and P, which is in the cotangent space to M at x, this is simply defined as 1/2 the magnitude P squared. Where here, this is magnitude of P squared is defined as G, I'll call it G star P, which then you could say is GP sharp P sharp. This is your Riemannian metric. So I'm sort of skimming through a lot of details here, but the point is that if you have a Riemannian metric, that's an inner product on the tangent space, you can dualize it to a inner product in the cotangent space that here I'm calling it, so it's referred to as Riemannian cometric, which means that we then have a norm on the cotangent bundle and so on and so forth. So if you take this specific Hamiltonian, because remember, Hamiltonian is just a fancy name for any function on the cotangent bundle. The result in Riemannian geometry, which I don't have a reference for offhand. I mean, I would maybe say Einstein manifolds by best, but that's overkill. Anyways, is that if gamma is a geodesic on a Riemannian manifold mg. Then one can relate this back to the Hamiltonian by saying then it is the projection of an integral curve of the Hamiltonian that I defined Hamiltonian on the previous page. So here what I'm saying is that you take this specific Hamiltonian, you go ahead and generate the Hamiltonian vector field and consider integral curves of this. The integral curves of this are curves in T star, but you can simply project those down to the manifold. And the claim is that all geodesics on a Riemannian manifold are of this form. You can also say for short enough length, it's true. Yes.
Can you explain about what is projection of the integral curve?
Yes, yeah, absolutely. Because I agree. I'm going a little fast. I agree. So in more detail. So let xh be the Hamiltonian vector field on T star m. So remember, this means you for this moment you're thinking of T star m as a manifold, sort of just forgetting m for a moment. So it means xh is a smooth section of T star m. It's a little strange, but it's fine. So then an integral curve of xh is a curve. I'll call it gamma tilde, where the tilde is trying to indicate to us that we're in the cotangent bundle. So it's negative epsilon to epsilon into the cotangent bundle, such that gamma tilde dot is always equal to xh. So it's just finding curves of a vector field. The weird thing here is that the vector field is on T star m. So then what happens is the theorem basically says that if gamma tilde dot is an integral, excuse me, not dot, gamma tilde is an integral curve. Actually, let me write it out. So if it's a curve, one can write gamma tilde of t is x of t, p of t. So x of t is always somewhere in the manifold, and p of t is a cotangent vector at x of t. So you're in that the cotangent space at that point. So then if this is an integral curve of xh, where h has to be specifically this Hamiltonian I keep mentioning, then gamma of tilde, which we'll define as the projection onto M of gamma tilde, which is a really fancy way of saying x of t. See, we're literally just taking this and ignoring the cotangent part, is a geodesic. And for G, the Riemannian metric from before. And I think the way I wrote the theorem on the last page was a little inaccurate. It's an if and only if statement on small enough intervals. I'm being sort of imprecise. But the point is that locally, this works. For short time, this always works both directions. So the point is, if you're interested in finding geodesics, okay, if you're interested in finding length minimizers for a metric, that means you want to find geodesics. If you want to find geodesics, you can do so by considering this Hamiltonian, which I'm going to try to consistently write in coordinates so that we actually have the expression there. So the Hamiltonian here is called the energy associated to the Riemannian metric G. Because remember, this double bar here denotes the cometric. This is for G. I do want to point out, in case you're interested in mathematical physics, it's called energy because if you sort of naively do this, and you define your metric to be well, the length of velocity vectors in like 3 space, the cometric is plugged into this actually gives you like 1/2 mv squared. It's cool. Anyways, so what does this have to do with us? Well, if you're familiar with Laplacians, this is the principal symbol of a Laplacian. So what do I mean by that? So we should actually now talk about that. But yeah, I wanted to start talking about that by motivating this. So the idea of Laplacians in general, you notice I do use plural. We don't have just the Laplacian. But the idea is, given a vector bundle, so I will have E over M. And let's say the space of differential operators. And yeah, of differential operators. Let's say smooth sections of, what's the best way to write this one down? I could say that this is the bundle of endomorphisms over E that's generated by covariant differentiation. So let's go with that. Endomorphisms of E and something like this. So what am I saying here? That is, if D is somewhere in here, morphisms, here, I'm just going to give this a name so I don't have to keep writing this. So for the space of differential operators, I'll give it like a cursive D. D, E. So if D is a specific differential operator, then we should be able to write D in coordinates. So let's say the sum from, okay, we need orders here. Let's say K equals 0 to, well, it's, let's go with, sorry, I didn't have this pre-written out, which was definitely a mistake. Let's write it as, here we go. I can write it as the sum over multi-indices up to order m. It's a nice way to express it. A alpha x partial order alpha partial x alpha, and I can explain this notation here. So what does this mean? The idea is that the covariant derivatives up to expression in terms of Christoffel symbols can be written like this. These alpha are multi-indices, alpha 1 dot dot dot, alpha m, yeah, alpha order of alpha, there we go, are multi-indices. And the whole point of this is just to give us a nice expression for differential operators. So in this context, then, if you've got the space of differential operators, you can define the symbol of a differential operator in the direction of a covector. So given a differential operator and a covector, so let's write this as T star at a specific point x over m. one defines the principal symbol sigma in the direction psi d to be, yeah, we can do it this way. I to the m sum over alpha equals m a alpha x psi alpha. So what am I talking about here? The idea is that psi d is meant to be a map from e at x to e at x. And this object, it captures the highest order properties of the differential operator. So yeah, I'll just write that. Captures the highest order properties of D. Great. So this is what I was sort of alluding to, and I feel like I don't have enough time to go into more detail about this. If you really want to do this properly, the idea is that you have to write sigma D out, something like, you can say something like this. Sigma D is actually the limit as t goes to positive infinity of e to the negative t. I need yeah, I can write this e to the negative tf d e to the tf, where here f has df equals psi. Okay, so the point of this is that the principal symbol captures in a specific way the important information at the highest order of a differential operator. And then one says that D is a generalized Laplacian if its principal symbol is precisely this. So why do we do this? Well, it's motivated by the original definition of Laplacian, but it's also motivated by the fact that this was exactly our Hamiltonian on the other page, right? Okay, so it turns out that in Riemannian geometry, what you can do is, given an orthonormal basis, oops, x1 or like xi, where I goes from 1 to n of the tangent space. You can do this pointwise, so it doesn't have to be globally defined. This defined as the sum is a generalized Laplacian. So this is called the sum of squares Laplacian. You want to be lazy? I'm just going to write Laplacian, but I mean generalized. And that's probably not surprising. We can't do this in sub-Riemannian geometry. The reason being is that we don't have an orthonormal basis of the tangent bundle. So all right, that doesn't have a orthonormal basis for the entire tangent bundle, only the horizontal bundle. So what you can do is you can just define a, you can write something like this. I guess I'll put a little SR here, is equal to the sum from I equals 1 to, let's say, m of xi squared, where xi from I equals 1 to m, which is the I'll say the rank of the horizontal bundle, is an orthonormal basis for H. You can do that, and it is a generalized Laplacian. But the problem is, given two orthonormal bases, which I'm just going to write xi and yi for H. One has to think about xi squared minus yi squared, right? Something like this. So unfortunately, well, this doesn't work. What I mean by that is that in Riemannian geometry, you show that under a change of basis, this might not be zero, but the information that's left over is of, well, first order. That will happen for sure. But also, it doesn't contain any of the geometric data that you're trying to capture. Unfortunately, in sub-Riemannian geometry, you can lose something. There is a solution, though. So in Riemannian geometry, you can actually pick a Laplacian that is associated to the metric in a nice way. One can define a Laplacian, delta, let's say, by the integral of delta f g d volume should equal negative the integral of f g d volume, where here this is the Levi-Civita connection. This is this definition then doesn't depend on your choice of basis. And you can show that it is of that form for any orthonormal basis up to first order terms, or sorry, up to zeroth order terms. A couple of problems in sub-Riemannian geometry happen right away, though. The first is that we don't have a Levi-Civita connection. And the second is that we don't have a volume form. So sub-Riemannian case. Well, the idea is that one can define d horizontal. I'm sorry, yeah, the horizontal covariant derivative can be defined. There's a couple different approaches to this. So the easiest approach is, in my opinion, is just to take projections of Levi-Civita if you've extended it to a Riemannian metric. In the cases where you can't extend it to a Riemannian metric, it's still fine. So it's a well-defined object that is not doesn't give us any problems. So I don't want to go too far into the construction of that because I've already taken too much time. But the trickier problem is the volume form. The volume is unclear. And the reason for this, I'll just say this in words, is that in Riemannian geometry, one takes d volume to be the wedge of the cobases, the dx1, dx2, dx up to n. But of course, you don't have a cobasis in sub-Riemannian geometry. However, turns out that the solution to this is actually very clever as well. And the solution works through what is called the pop measure. I was thinking to actually go ahead and give a full explanation. Yeah, you know what I'm going to do? I'm going to give the two theorems without proof. Next time I talk, I can actually give the construction of this on a contact manifold, which then connects to the Kähler geometry. So the idea is we need two lemmas, which I'll actually state properly. So if E is an inner product space, and pi from E into V is a surjection. Then this induces an inner product on V. So if you have some experience with tensor algebras, that shouldn't be a surprise. It's not that hard to show. The other more interesting example or lemma that we need has to deal with filtrations. So the idea is if we let E be a vector space with dimension n and a filtration. Let's write it like this. I should say by linear subspaces if that's not clear. F1 is F2 is dot, 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 all the way up to F, let's call it L equals E. So if you're not familiar with filtrations, the idea is that this is like this is a flag of linear subspaces, such that there are a finite number of them. That is essential, and the last one is actually the whole space. Then go ahead and define a gradation of F to be the direct sum where you quotient sequentially. So here we take F1 to start, and then you do F2 quotient F1, just keep going all the way up to FL quotient FL minus 1. So this is called associated graded vector space, however you want to do this. Well, the interesting thing, oh, that's not an A. One can show that there is an isomorphism between the exterior algebra of full degree. This is important, that has to be the volume forms here, and the exterior algebra of, sorry, the co-space, and the exterior algebra co-space of the gradation here. So of course these are isomorphic because they have the same dimension, but they're canonically isomorphic. This is essential. That's actually a little bit harder to prove, actually. But well,
Just
what
to
does
be
this have to
sure,
do?
I'm sorry, Gianmarco.
Yes.
So is this an algebra isomorphism, then not just a vector space isomorphism?
No, it's a vector space isomorphism.
Oh, okay. Yeah.
Yeah, because we don't have an algebraic structure on E. Correct.
Oh, yeah. Okay. Thank you.
Yeah, it's a good question. You could basically argue this is how you make an algebraic structure on E.
Mhm.
Yeah. All right, so instead of going to the construction and how we do any of this, let's talk about why this actually matters to us. So let's go ahead and consider the gradation of H, our horizontal bundle. So here, Fi is equal to the collection of degree I brackets. So what do I mean by that? I need a 1 there. 1 bracket. Yeah, I need more room. So the idea is that we define these Fi's by taking I brackets of vector fields, of horizontal vector fields, I should clarify. So xi minus 1, xi, where all of the xi's are horizontal vector fields. So it should be clear that this is a filtration because the degree I brackets contain the degree I minus 1 brackets. The thing that you could argue is actually an essential property that comes from being a sub-Riemannian manifold is this right here. Why do we have a finite number of steps? Well, so FL, which is equal to F times the sub-Riemannian step. So yeah, I'll just write step for that. That is the number of brackets you need to generate the whole thing is in fact the entire tangent space. I should probably say smooth sections of the tangent space, but I'll put it a little lazy. This is exactly the condition that we introduced before because of this is the bracket generating condition. That is like the essential definition of what it means to be a sub-Riemannian manifold. So great, we have a gradation of the horizontal space. So we satisfy this, and we have a submersion where we take the tangent space and submerge it into our horizontal space. So what does this accomplish for us? Oh yeah, I mean I should clarify that F1 is F1 is exactly the horizontal space. So what's the conclusion here? If you use the two lemmas together, together give a volume form. on Tm that is determined purely sub-Riemannian in a sub-Riemannian way by the sub-Riemannian metric. This is called the Pops measure. Yeah, I would really like to construct this explicitly for contact manifolds. I'll do it another time because I've already talked way too long. But okay, so where does this leave us? But I will mention there are many other ways to construct volume forms on sub-Riemannian manifolds, but there's really good reasons, good arguments you can give for why this is natural. Maybe one of the easiest is that if you look at the sub-Riemannian structure on Lie groups where these occur, that it is the unique left invariant Haar measure or something like this. Yeah, I have to be careful with that. It's something like this. There's a uniqueness of left invariance. Anyways, so what do we do with this? Okay, so then the sub-Laplacian on a sub-Riemannian manifold is defined using the Pops measure. So we say exactly, I'll write this Laplacian sub R F times G D, I could say d volume pop if you like, is defined as equal to this, where this is the horizontal gradient. D volume pop. And that solves the problem. Oh, excuse me, there's a negative sign here. That negative sign is important. Yeah. There's a lot more to say about this, but I will say that it is a generalized Laplacian, and because of that, its principal symbol does give you geometric information, but I should emphasize that it's not elliptic. It can never be elliptic. So just to be clear here, a second order, so D second order differential operator, we say the following. Elliptic if its principal symbol is injective away from 0. Okay, so if you take any cotangent vector here, not 0, then the principal symbol should be elliptic. In Riemannian geometry, the Laplacian is an elliptic operator. We say it's hypoelliptic if it meets the following condition that I want to say precisely. If the equation LF equals U, with U given and compact support. I'm sorry, I wrote L, looking at the notation of this thing. DF equals U. Compact support always has unique solution with compact support. Yes. So the idea is that if you're trying to solve a wave equation or a heat equation or something to this effect, you expect that if the initial conditions have compact support, that the solution should exist uniquely and have compact support. The Riemannian Laplacian is elliptic. The sub-Riemannian Laplacian given by the pop volume here is hypoelliptic, but never elliptic. And if it's not clear, excuse me, when I say this, that's the wrong way to put the arrow, I think. It depends on what you mean by the arrow. Ellipticity implies hypoellipticity, but not the other way. So yeah, yeah, I can talk more about this if it's interesting. I'll give the construction on contact manifolds, and I can prove hypoellipticity and these other lemmas, but I've covered more than enough. Thank you.
Yeah, thanks for a great talk. So any questions or comments?
Actually, I have very basic question because it's been a while that I used the notion of connection in my research. So in the equation, the characterizing the Laplacian, on the right hand side there, is a factor that the connection is applied to a function, how could one make sense of that thing, the connection? How can the connection be applied to a function?
That's
Mhm.
that's a good point. So what I wrote there works. It maybe is sloppy notations. There's two ways to interpret it. If you apply a connection to a function, in principle, you should then be getting a covector, which is the same thing as just taking the exterior derivative of the function.
Mhm.
The reason that I don't want to say that is because that's what I said is true for Riemannian geometry, but in sub-Riemannian geometry it's a little bit more subtle. So the horizontal connection applied here does give you a covector, but it's not quite the same as taking the differential. Hence, we
Okay.
want to distinguish. So then the inner product I have over there on the right-hand side should be understood as the cometric.
I
And in
see.
fact, honestly, the book, which by the way I highly recommend it, it's Richard Montgomery's Tour of Sub-Riemannian Geometries. But in that book, they make the argument that it's actually more natural to define a sub-Riemannian structure by the cometric rather than the metric. And the reason for this is that a lot of this geometry works better from the cotangent bundle, as in seeing the Hamiltonian.
I see.
Yeah. But yeah, so that's, I hope that's answers your question. Those are covectors.
Yeah, thank you for clarifying.
Yeah, so let's take off 5 minutes and let's just finish, let's say, conversation and presentation by Dr. Liz talk. So let's just have a break for 5 minutes.
Thanks.
All right, so yeah, can you share your screen?
All right, let me just try to share my screen. Can everyone see my screen?
Yep.
Okay, perfect. Yeah, I'm ready to speak.
Okay, let us start. Okay, so the last talk is the talk of the family. So yeah, thanks for the learning.
Okay, so can I start?
Yeah, you can start. Yeah, thank you.
Oh, okay, yeah. Okay, so thank you for your nice talks, and today let me tell you briefly tell you the meaning of the trace, the normalized trace on the left-hand side of the Kant's trace theorem the last time. Last week, I explained the meaning of this space, the L1 infinity, which is called the weak trace class, the operators, the ideal of the weak trace class operators. And today, I will briefly tell you how to construct the trace on this space. Okay, so before I proceed, last time that I told you that the construction or the properties of the eigenvalue sequences and the singular value sequences of the given bounded linear operators or the compact operators, and by using the sequences, the properties of the sequences, we can characterize those compact operators by the decaying property or the summability of the singular value sequences. So if the singular value sequence of the given the compact operator satisfy this summability condition for the given the p greater than equal to 1, then we say that the operator, the compact operator T, belongs to the Shetland P ideal of compact operators. And if the singular value sequence satisfy this decaying property, then we say that the operator T belongs to the weak Shetland P ideal of compact operators. And for P equal 1, then the L1 infinity is called the ideal of weak trace class operators. And here is another space I didn't mention the last time. So if the singular value sequence satisfies this property, then the corresponding ideal, the correspondence is given by the Calkin correspondence I explained you last time, is called the Dixmuir-Markov ideal. So I'll tell you the inclusion properties between these ideals later on. But before then, let me explain you the general theory of the functional analysis.
So there's a question from Gianmarco in the chat.
Okay. That what do weak trace class operators that are not trace class look like? Do you have any simple example? Yes, we had the simple example that I will tell you later on. So yeah, so well the simplest example of the weak trace class operator is I explained you how to create the diagonal operator if we have any sort of the sequence. So if one considered the harmonic sequence, the sequence 1 and 1/2, 1/3, and so on, then well we can consider the diagonal operator that corresponds to the harmonic sequence, and if we take the sum of these eigenvalues, then as you already know, this result in the basic analysis, it diverges, so it cannot make the ordinary trace of the diagonal operator of the harmonic sequence does not make sense. But the harmonic, the diagonal operator of the harmonic sequence belongs to the weak trace class operator, the ideal of weak trace class operator. So it should be dealt with the traces on the ideal of weak trace class operators. Maybe I think this would answer Gianmarco's question.
Yeah, that makes a lot of sense. Thank you.
Yeah. All right. So, but there is another space which is called the Diximier, the Markov ideal. Is defined by this decaying property of the singular value sequence. And before I proceed, let me briefly tell you something on the functional analysis, which is not very common. This a little bit exotic theory. So I think many of you are quite familiar with all this setting. Is very similar to the definition of the map norm, but the only one difference is that now we allow there is a constant k which is greater than or equal to 1, and if k is equal to 1, then this map is called the norm on a vector space, as you already know. But in general case, the map satisfying this property is called a quasi-norm on the given vector space. Okay, so the quasi-normed vector space can be seen as a topological vector space. So we can induce the topology on E by using this quasi-norm. Well, the detail is a bit complicated, but the topology is characterized by declaring the neighborhood of the origin by using the open balls under this quasi-norm. So the difficult point here is that due to this constant k, in general, these open balls are not a convex set. So there is a possibility that if one chooses 2 points and draw a line segment connecting the 2 points, there is a possibility that some part of the line segment is kicked out of the open ball. But fortunately, it can be shown that this topology is metrizable. Okay, so it's not very exotic because at least it can be seen as a metric space. But there are in the many arguments, the general theory of the functional analysis, which one can learn in the general graduate course, does not apply. So one should be very careful to derive the theorems of functional analysis in case of the normed space. But at least it is metrizable, and if given the vector space is complete with respect to this topology, then we say that it is a quasi-Banach space. And we say that if there is a two-sided ideal of the space of bounded linear operators of the separable Hilbert space H equipped with a quasi-norm or norm, then we say that this J is a quasi-Banach ideal, or if this is just a norm, then it's just called a Banach ideal. If J is a quasi-Banach space or the Banach space with respect to the quasi-norm or norm, I forgot to add quasi with parentheses right here. And if there is the norm on J satisfy this property, here the norm of A and B is the usual operator norm on the space of bounded linear operator. If this estimate is satisfied, then we say that J is a quasi-Banach ideal. Okay, and every two-sided ideal of LH contains the ideal of finite rank operator, and all the examples I gave above can be seen as a quasi-Banach ideal or Banach ideal. Okay, so the LP is a Banach ideal with respect to the norm, and the closure of finite rank operator. Here I will denote the closure of the finite rank operator inside the given ideal J by this notation. And here this 0 should be replaced by P. But in the case of the weak-shortened P ideal, in general, it's not the Banach ideal. The quasi-Banach ideal would arise, so one should be careful. So in the case of the weak-shortened P ideal, if we use the estimate characterizing the weak-shortened P class operators to define the topology of the weak-shortened P ideal, then it is well known that this is a quasi-norm because it satisfies this inequality. Okay, but for P greater than 1, this quasi-norm is equivalent to the norm. It can be shown that this one is equivalent to the norm. So in the case of P greater than 1, then LP infinity is a Banach ideal with respect to this norm. However, L1 infinity, the weak-shortened class operators, this space cannot be seen as a Banach ideal. It's a quasi-Banach ideal with respect to the norm, the quasi-norm, defined by this equation. Okay, and lastly, the last ideal I mentioned, the Diximier-Markov ideal, is a Banach ideal with respect to this norm. Well, I'm omitting the tons of details, and the fact I would like to mention is that if the P and Q have this relation, then there are strict continuous inclusions. Okay, so LP is included inside the closure of finite rank operators of weak P-shortened class operators, and this closure is not exhaustive inside the LP infinity. So this is also the strict inclusion. And if Q is greater than 1, then LP infinity is included inside the Q-shortened class operators. And in particular, for P equal to 1, then we have this inclusion. Well, these inclusion are the particular case of the inclusion described above, but it is well known that the Diximier-Markov ideal is slightly bigger than the ideal of weak-shortened class operator. And if Q is greater than 1, we have this strict inclusion.
Maybe I'm misunderstanding the notation. I apologize. In this first line of strict inclusions, for 1 is less than or equal to P, is that middle inclusion saying that LP infinity's closure is a strictly included inside of LP infinity? This is...
Oh, no, this is the closure of the set of finite rank operators.
Right. Okay. There. I'm glad. Thank you.
Yeah. So. Okay. So I know this. There is a lot of plenty of the new information to you, but let me just proceed to reach at least to some conclusion. So here, given the two-sided ideal of the LH, then we can define the subspace of J in this way. This is the span as a vector space of this element. Here, the T is the element of the ideal J, and A is just the general bounded linear operator. And ideal property of J say that says that this is the also element of J. So this can be seen as a vector subspace of the ideal J. Okay, and so what is the trace? The definition of the trace in my context, a linear map. So let the J be a two-sided ideal of the LH, and EB is a linear subspace containing the commutator subspace of J. Okay, so the E lies between the commutator subspace of J and the two-sided ideal J. Okay, then a linear map phi from E to another vector space is called the trace if phi vanishes on the commutator subspace. So you already know that the definition of the trace usually concerns the vanishing on the commutator, the subspace, but I applied the definition in the setting of the bounded linear operators. Okay, and in order to construct some useful trace by using the eigenvalue sequences of the compact operator, I need to collect some the basic properties of eigenvalue sequences and the singular value sequences. And all of these inequalities are highly non-trivial, but let me just collect the result on them. So if T is a compact operator, then it's well known that here lambda J is the eigenvalue sequences I mentioned last time, and mu J is the singular value sequence, and the eigenvalue sequence and singular value sequence satisfy this inequality. Okay, so and another thing is that one should also notice that there are many choices of eigenvalue sequences for the given compact operator, and any eigenvalue sequence of T satisfies the same inequality. And if we take the sum of two weak trace class operator, then its eigenvalue sequences satisfy this property. Here I use the usual big O notation in the mathematical analysis. And if we take the two different eigenvalue sequences of T, then the sum of first n terms of the two different eigenvalue sequences satisfy this property. And there is another proposition which characterizes the commutator subspace of the ideal of the ideal of the weak trace class operator. This is the property which characterizes the commutator subspace of the ideal of the weak trace class operators. Okay, so how can we construct the trace on the ideal of the weak trace class operator? Okay, so here I didn't write the definition of the notion of the C-star algebra, but it's the topological algebra, the normed algebra, satisfying the certain conditions, which is the main object in the field, the operator algebra. But anyways, the normed algebra satisfying certain completeness property, and it's well known that the L infinity, the space of the bounded sequences, becomes the C-star algebra with respect to its supremum norm, and it's the algebra structure. The product is given by the pointwise product of the bounded sequences, and here the C naught, the space of sequences converging to zero, forms a closed ideal of this C-star algebra, closed with respect to the supremum norm. Okay, and so we can consider the quotient C-star algebra as it forms an ideal. Okay, and by using the Key-Fans inequalities right here, we can say that any eigenvalue sequence of T satisfying this inequality. And well, this estimate is quite trivial by comparing the log n and the log n plus 1. And this is exactly the Diximier-Markov norm on the ideal of Diximier-Markov operators. And well, I also didn't prove that, but due to this strict continuous inclusion, we can also estimate the Diximier-Markov norm by the quasi-norm on the weak trace class operators. And here the left-hand side, the log n over 1, does not make sense in the case that the n is equal to 1. And here I'm just adopting the convention that the 1 over log n is 0 or n is equal to 1. Okay. So all this estimate shows that this sequence is a bounded sequence. So it belongs to L infinity. Okay. And if lambda j t and lambda j prime t are two different, here, sorry, there is a typo that this should be replaced by the different eigenvalue sequences of t. I told you that there are many choices of the eigenvalue sequences for a given compact operator. And then we know by this property that if we divide both the left-hand side and the right-hand side by log n, then we get this property. Okay, so here the point is that if we choose the two different eigenvalue sequences of t, then the corresponding sequence constructed via this procedure yields different sequences in L infinity. Okay, but due to this property means that if we subtract this sequence by this sequence, then it converges to 0 if n goes to infinity. Okay, so if we have the two different eigenvalue sequences, then the sequences produced by this procedure yields a different element in L infinity, but those two sequences yield the same element in the quotient C-star algebra because their difference belongs to C0 as they converges to 0 as n goes to infinity. Okay, this is the most important part of my the talk today. Okay, so now we get a well-defined map from L1 infinity to this quotient C-star algebra. It's defined as the class of this sequence, the equivalent class of this sequence in this quotient C-star algebra. Okay, and it's well known that this maps the positive element, the positive operator, to positive sequence in this C-star algebra, and this tau map vanishes on the closure of finite rank operators inside L1 infinity. In particular, it vanishes on L1, the trace class operator, because this L1 is included in the L1 infinity sub-0. Okay. And most importantly, this map is a trace in the sense of this definition. Okay. And all those properties can be derived from all these technical lemmas and proposition. This lemma is also for the additivity of the trace map. Okay, and how can we construct a scalar, or some useful number by using this trace map? Well, in order to do that, then we need to use sort of the linear functional, a linear map from this sister algebra to the complex number field. But we also need some sort of the normalization, the property, because in order to study the trace, then if one has constructed one trace, then it's the scalar, the theory on another trace created by the scalar multiple of the already constructed trace is quite trivial. So one need to just fix one trace among all the scalar trace by using the sort of the normalization property. So we need the condition that the linear functional, we will use the maps, the identity in the unital sister algebra to 1. Okay, and any positive linear functional on the unital sister algebra since 1 to 1 is called a state on A. Okay, so whenever omega is a state on the quotient sister algebra, the L infinity over C0, it's also the deep functional analysis, but by using the Han-Banach theorem in the functional analysis, one can construct plenty of state on the quotient sister algebra. I will omit that theory for today. And so by using the canonical projection, then one can construct a linear functionals on L infinity like this. Okay, and this linear functional, the limit sub omega, is called the extended limit. I will tell you the reason later on, because this is sort of the generalization of the usual concept of limit in the mathematical analysis. Okay, so let's suppose that the A is a bounded sequence. Then this is the well-known property from the elementary mathematical analysis. All the entries of the sequence is bounded by the lim inf and the lim sup of the given bounded sequence. And as the sequence is bounded, there is no worries that the both of these numbers are the real numbers. So by using the positivity, because I assume that the definition of state that is the positive map, it sends a positive element of given sister algebra to a positive number. So by using the positivity, we can always assume that the generalized limit of this bounded sequence satisfy this boundedness property. Okay, so from this inequality, we can deduce that the generalized limit has the value L for all states on this sister algebra is equivalent to the statement that the sequence converges to L. Okay, so in this sense, the limit of omega is called the generalized limit. Okay, so by using the extended limit, by composing tau map defined here with omega, in other words, as the tau map is the equivalence class of this sequence inside this quotient sister algebra, then we can evaluate the generalized limit, the extended limit of this sequence. Then we can define some sort of trace associated with the state, a given state omega. And this trace is called the Diximia trace associated with the extended limit omega, or the state omega on the quotient system algebra L infinity sub C0. Okay, so any questions so far? Okay, so let me continue on. All right, so then that, and it's well known by this property is almost immediate from the properties on the tau trace map. Well, the Diximia trace is a positive continuous trace, and it vanishes on L1 infinity sub 0. Okay, and then the natural question which would arise is that I told you that there are plenty of the states on this quotient system algebra. Well, I won't tell you the detail, but the cardinality of the set of such state is also verified in the literature. Then if there are many traces, then the dependence of this Diximia trace on the choice of the state omega, it would be the natural question. Okay, but we are most interested in the linear operator, which does not depend on the choice of an extended limit or the state omega on the quotient system algebra. Okay, and it forms a subspace of the weak trace class operator, and we will denote such a space by calligraphic M, and the element of this space, the linear operator, whose value does not depend on the choice of an extended limit, is called measurable. Okay, and the Professor Alan Kohn defined the notion of the non-commutative integral in this way: non-commutative integral of the measurable operator, as its value of the Diximia trace does not depend on the choice of an extended limit. We can choose any extended limit for such operator. Okay, to define the notion of non-commutative integral in the sense of Alan Kohn. Okay, so unfortunately for today, I cannot give you any concrete example of measurable or the non-measurable operator. There is also an example of non-measurable operator whose value of the Diximia trace is dependent of the choice of the extended limit, and the construction of such operator involves the theory of pseudo-differential operators. So I'll postpone the construction of such operators to my talks the next time. Okay, but some basic properties of the measurable, the space of measurable operator is that it forms a closed subspace of the L1 infinity, and it contains the commutator subspace of L1 infinity and the L1 infinity 0. And this is also a positive continuous trace vanishes on this space. Okay. And now I have only the one last comment. Do you have any question?
Just a quick question about that last statement. When you say that it vanishes on L1 infinity 0, is this exactly the kernel, or is this contained in the kernel?
Well, I'm not sure, but this me just think about it.
If it's not obvious, it's fine. I just wasn't sure if that was your implication by saying advantages on the space.
Oh no, I think it's exactly the kernel of although it's hard to explain that for today, but well, so I will tell you some comments on this later on after I finish.
Totally fine.
Yeah. Okay. So yes. So let me just tell you something. So maybe you wonder why I told you something on the quasi-Banach space or the quasi-Banach ideal. Well, actually the continuity of the tau map or the Dixmuir trace, well, it essentially depends on this estimate to show that the boundedness, the supremum norm of this sequence is given by the quasi-norm on the space of the trace class operators. But as you can see in this estimate, it can also be estimated by the norm on the Dixmuir-Markov ideal. And in the early stage of this research, actually all researchers worked on the ideal of the Dixmuir-Markov ideal instead of the weak trace class operator, because at the first glance it's more convenient to work on the Dixmuir-Markov ideal, because unlike the weak trace class operator, the Dixmuir-Markov ideal forms a Banach ideal. The property, the L1 infinity, does not have this, only forms a quasi-Banach ideal. Then if this forms a Banach ideal, then why one should consider the quasi-Banach ideal, the L1 infinity? Well, and here is the main reason. This kind of property was revealed about 10 years ago. So, but there are traces on L1 infinity. I actually constructed Dixmuir traces on L1 infinity, but there are traces on L1 infinity which cannot be seen as a Dixmuir trace. So there are traces on this space which cannot be constructed via this recipe. Okay. But this construction of such traces is quite similar, but one should refine or modify this. It basically used the similar idea, but one should modify some of the arguments. But so I just decided to write the Dixmuir's original construction, because the modified argument involves more functional analysis, and I don't want to bother all of you on that point. But I can just tell you that the modern, the refined construction of all these traces, including the Dixmuir traces and non-Dixmuir traces, is quite similar. And as the point I'd like to address is that many linear operators encoding the useful geometric information belongs to L1 infinity. Okay, so as L1 infinity belongs to the Dixmuir-Markov ideal L1 infinity with parentheses, so the linear operators encoding useful geometric information belongs to this space, and consequently this space as well. So we must, in order to get some useful number, the scalar, by using those traces, we must take care of computing the value of the Dixmuir traces of this operator, and as well as non-Dixmuir traces. All traces, and some of them are the Dixmuir traces. Okay, although unfortunately I couldn't show you the explicit construction of all those traces. Okay, and another definition here is that a trace is called normalized if it sends the diagonal operator of the harmonic sequence to 1. And all the dissimilar traces are normalized traces because due to this the normalization property of the definition of the state. Okay, and so as there are the more traces than the dissimilar traces, in order to study the independence of the choice of the traces, as there are more traces, we need the stronger definition on that the independence, which is called the strong measurability condition. So a linear operator is strongly measurable if the value of trace is independent of the positive normalized trace on L1 infinity. And we denote the space of strongly measurable operators by this notation. And so I have the two more comments, the last comments on my lecture. So here in the Kohn-Trace theorem, so on the left-hand side, this means every normalized trace on L1 infinity, including dissimilar traces, the TR sub omega is the subset of the set of all normalized trace on the L1 infinity. Okay, so this is what I meant by the normalized trace on L1 infinity. And another comment, the last comment is concerning the Gianmarco's question. So this is the purely infinite dimensional phenomena, the infinite dimensional, the construction only available in the infinite dimensional setting, because all these the normalized trace I mentioned, including the dissimilar trace, they vanishes on the L1 infinity sub 0, the closure of the finite rank operators inside the L1 infinity, and it has the space of trace class operators as a subspace inside. Then on the set of trace class operators, there is the trace, so-called usual trace, by taking the sum of all the singular values there. So, but for the traces I constructed on this space, then all that the traces annihilates on this space, in particular this space. So what I want to say is that such traces cannot be observed in the finite dimensional setting, because these kind of traces kills all finite rank operators. So it only works in the purely infinite dimensional setting. And next time I will tell you how to relate the operators considered in the geometry can be related to all these class of operators and the traces on this ideal of the weak trace class operators. So thank you very much for your attention.
Yeah, thanks. So let me stop the record.